All right, so in the previous class, we had learnt about what is a vector space, and we saw that a vector space is basically a non-empty set. And then you define two things, what is called the vector addition and scalar multiplication. And we want certain conditions to be satisfied, certain properties to hold for vector addition and scalar multiplication. And then should be something, what is called the distributive law, to relate all of that. Fine. So whatever those conditions were, they were obtained through basically what happens for the vectors in R3 or what happens for matrices as far as matrix addition and scalar multiplication are concerned. Fine. Now I would like to look at what I call a subset of that vector space. So in mathematics, we have a set, then we have a subset. So similarly here we have a vector space. So I would like to know when can I say a subset of the vector space is also a vector space. So we want to talk of what is called a vector subspace. So definition, vector subspace. So what we need is that we should already have vector space V. So let this be a vector space and W a subset of V with W non-empty. This is very, very important. It has to be a non-empty set. Non-empty, very important. All right. Then W is called a vector subspace of V over F. Also important thing here, we are saying it is vector subspace of V. So it is a subset of V and it is a subspace as far as F is concerned. The F does not change. Earlier the vector space V was also over F. Here also you have the same F. There is no change as far as the scalar field is concerned. It has to have the same thing. All right. Then W is called a vector subspace of V over F if W is also a vector space. But vector space, but I'm not allowed to change the vector addition and scalar multiplication. And or with respect to with vector addition and scalar multiplication inherited from V or coming from V itself. So what we are saying is that I have two elements U and V belonging to capital W. This is a subset of V. Fine. So do your calculations in V. So look at U plus V in V, compute it, and then we want U plus V to be an element of W itself. All right. So the calculation that we are doing vector addition is in V. We are not doing anywhere else. The calculation is not supposed to change. I cannot change the rule of vector addition. All right. Similarly, if I take alpha belonging to F, look at that V is a vector space over F, then W is a subspace over F itself, the same F, there is no change. All right. And I take U belonging to W. Again, this is a subset of V. Alpha dot V makes sense in V itself. So I'll do this calculation. So calculate and want and need alpha times V to belong to W. All right. Fine. So my calculations are done in V, but we want that those calculations, the final result that I get should be an element of W itself. Is that okay? So this is very important. So note, I'll just state it once more. Note 1, W is non-empty. This is very, very important. 2, we are not allowed to change. We are not allowed to change the two operations. All right. Change the set of scalars, comma, the vector addition I cannot just change it. It has to come from V addition and the scalar multiplication and the scalar multiplication. All right. So I'm not allowed to change it. These two things have to be computed, computed in V itself. All right. This is very, very important. You cannot change things. Fine. So let's look at examples. So to do the examples, I would look at what are matrices and do things there itself. All right. So I have got A, which is M cross N matrix. Fine. Over say real numbers. So our notation was M of M cross N of R. This was our notation. Set of all M cross N matrices. Then there are 4 fundamental subspaces which are related with this. So let me write that out. So the what are called 4 fundamental subspaces. 4 fundamental subspaces of subspaces related to F, related to A. So I'm fixing this A and I'm looking at this. All right. So what is called the column space of A, which is equal to all X belonging to, see, I'm allowed to multiply AX. So all X belonging to column space. So I think you'll get confused if I write like that. So let me write it AX, X belonging to Rn. Fine. So I wanted to write it as all B belonging to Rm, so that Ax is equal to B has a solution. So this is the way you could like, whatever way you want to understand, you can write it this way. Fine. Then there is a notion of what is called the null space of A, which is all X belonging to Rn, such that Ax is 0. All right. So all the elements which are being sent to 0 vector. Fine. This is called the null space of, I have written null space. This is called the column space. And column space, if you see, it is a subset of Rm. Ax is an element of Rm. So this is a subset of Rm. This is a subset of Rn, because I'm looking at X here. Fine. So this is A for me, this is B, this is C. Now what is called the row space of A, which is same as column space of A transpose. All right. So when I'm looking at complex, I'll have to look at A star and things like that. Fine. So this is column space of A transpose. This is nothing but A transpose Y. And where should Y be? It should be in Rn. Fine. And so there is a subset of Rn as such. Fine. D, left null space. So here I have null space of A coming from column space of A. So left null space will come from column space of A transpose of A. So this will be equal to, so I've written X here, all let it be Y belonging to, I should have written differently. Fine. So I have to look at Rm here, such that A transpose Y is 0. All right. Fine. So I would like you to see that this is a subset of Rm here. This is a subset of Rn. So what I want you to see here is that look at this and this. They are subset of Rn. Fine. Whereas this and this, they are subsets of Rn. Fine. So I've got two subsets coming from different places. One is looking at null space of A and row space of A. These two are coming from Rn. And what is column space of A and left null space, they are coming from Rn. The question is, are they related? What are the things that we can do with them? All right. Because when we have a data, every data is written in terms of matrices. So can I relate these information? So that's the basic idea. Fine. So I've already written left null space and so on. So I'd like you to understand them and we'll proceed further with those ideas. All right. So let's look at some examples to understand it better. So I'm going to start with in R2, or I'm looking at a matrix A, which is 2 cross 2. Right. So all these spaces that I look at here, since I'm looking at 2 cross 2, all of them, they will be subset of R2 itself. All right. So I'm going to take different matrices. My first matrix is 1, 3, 2, 6. So if I look at, by definition, column space of A, row space of A, null space of A, and left null space of A, all of them are subset of R2 itself. All right. So let's compute them one by one and see what I'm tracking of. So column space of A is AX, X belonging to R2, which is same as alpha beta, A times alpha beta, which is alpha and beta belonging to R. So just multiply the matrix multiplication. It is alpha times 1, 2 plus beta times 3, 6, alpha beta belonging to R. I would like you to see that this is same as alpha plus 3 beta times 1, 2, alpha beta belonging to R. And verify that this is nothing but this is equal to a line. I'm writing live here, a line in R2 passing through 0, 0 and 1, comma 2. Fine. You can put transpose so that you look at in terms of vectors. All right. So maybe as this is just, let me write it like this. Because if I take alpha and beta to be 0, I get 1, 2. Fine. If I do not take it, if I take something else, I'll get, so if I take alpha to be 1, beta to be 0, I get 1, 2. So it passes through 1, 2. It will also pass through 3, 6, 4, 8, and so on, all multiples of 1, 2. Fine. So this is my column space of A. What is null space of A? Let's look at this. So null space of A is alpha beta belonging to R2, so that A times alpha beta is 0, 0. This is what I need. Fine. That's the definition of null space of A. This is same as alpha beta belonging to R2, such that A times alpha beta. So I'm looking at alpha plus 3 beta is 0 and 2 alpha plus 6 beta is 0, which is same as alpha beta belonging to R2, such that alpha is equal to minus 3 beta, which is same as, just let's replace alpha by minus 3 beta, minus 3 beta comma beta, beta belonging to R, which is same as beta times minus 3 comma 1, beta belonging to R. Fine. So it is a line passing through 0, 0 and minus 3 comma 1 transpose in R. All right. Fine. So what we see is that they are lines. Both of them are lines. And at present, we do not see any relationship between the two. The only thing we can see is that this is a line, this is another line. They are not the same line. So I can represent every other point in R2 using these two. That's the only thing I can see. Let's compute now the row space of A. So row space of A is nothing but column space of A transpose. So this is same as A transpose times alpha beta. So A transpose is 1, 3, 2, 6 times alpha beta belonging to R, which is same as, just look at here. So this is same as alpha times 1, 3 plus beta times 2, 6, alpha beta belonging to R, which is nothing but alpha plus 2 beta times 1, 3, alpha beta belonging to R. So a line passing through 0, 0 transpose and 1, 3 transpose with R2. All right. So this is what is important. That now let's look at these two things. All right. So null space of A, if I look at null space of A, it is a line which passes through 0, 0 and minus 3 comma 1. So look at the slope of this line. Look at this. These two lines are nothing but they are perpendicular. So what we see is that null space of A and row space of A, they are perpendicular to each other, at least in this case. Can we prove it for the general setup also? That's the idea that we would like to look at. Can we prove it for Rn as such? Fine. So that will come to afterwards when we look at inner product space and things like that, or maybe the fundamental theorem of linear algebra. But I would like you to see that such a thing is there because minus 3 comma 1 dot product with 1 comma 3 is minus 3 plus 3, which is 0. All right. So here in this example, what we see is that null space of A and column space of A are perpendicular to each other. Is it true in general? Fine. I have not computed the left null space. Let's compute the left null space now. Left null space. So of A. So this is nothing but again alpha beta belonging to R2, so that A transpose of alpha beta is 0, 0. So this is same as alpha beta belonging to R. So the A transpose of alpha beta. So it is alpha plus 2 beta is 0 and 2 alpha, sorry, 3 alpha plus 6 beta, 3 alpha plus 6 beta is 0. So I would like you to see that this is same as alpha beta belonging to R, such that alpha is equal to minus 2 beta. And therefore what we get here is alpha is minus 2 beta, beta remains as beta, beta belonging to R, which is same as beta times minus 2 comma 1, beta belonging to R. So a line passing through 0, 0 and minus 2 comma 1 transpose in R2. So I'd like you to see that. Let's look at this part. Copy. So if I look at column space and the left null space, so let me write it here. So this was our column space of A. This is what we had seen. So again, note here that these two are perpendicular. The vector 1, 2 is perpendicular to minus 2 comma 1. All right. So what we see is that there are two subsets, they are perpendicular, another two sets which are also perpendicular. So is it true in general? That's one has to understand. We'll come across it afterwards. That yes, they are indeed so. Fine. But we'll have to prove it. Let's look at another example. So I have taken A as this. I take another matrix B as 1, 2, 2, 4, or say 2, 6 here. So in my notes I have written it as 1, 3, 2, 4. 1, 3, 2, 4. Fine. I would like you to see that if I want to compute column space of B here, it is 1, 3, 2, 4 times alpha beta belonging to R. So this is turns out to be, looking at alpha times 1, 2 plus beta times 3, 4, alpha beta belonging to R. Now this matrix is an invertible matrix, and therefore you can see that we'll get whole of R2. Okay. So the question is, why do you get whole of R2? So let's take any point. So let x comma y be any point in R2. Question. X comma y transpose can be represented by the vectors 1, 2 and 3, 4 if the system A times alpha beta is equal to xy in the unknowns alpha and beta has a solution. All right, that's what we are asking it. That question is xy transpose can be represented by the vector 1, 2 and 3, 4 if the linear system this in the unknowns alpha and beta has a solution. The answer is yes, it has a solution. Yes, it has a solution, and the solution is given by, and the solution is given by alpha beta is equal to A inverse of xy. So for example, if you give me xy as 1, 2, then the answer is alpha is 1, beta is 0, and things like that. Try to solve it for yourself and verify for yourself. All right. So I'd like you to see that column space of B is this, which is also true of the row space of B, because again it is the same thing. Row space of B is same as column space of A transpose. So this will turn out to be R2. Spend some time and try to solve it yourself. Fine. Null space of B will be same as left null space of B, which is nothing but the 0 vector. So again you can see that row space of B is perpendicular to something, and column space of A is perpendicular to the null space of B, and things like that. Fine. So I wrote it wrongly. It should have been B here and B here. So as usual, here also I must have written wrongly. So it should be B here. Write B there. No, so that was the reason. All right. So I forgot about B. Right. As usual, B here. Fine. So you have to be careful. I do a lot of mistake. Another example is C. I take the matrix C as 0, 0, 0, 0. So I would like you to from here imply that column space of C is same as row space of C, which is just the 0 vector, and the null space of C is same as left null space of C, which is R2. Fine. So I'd like you to try that out yourself and then understand it. Fine. This is important. So you should spend some time yourself. Importance definition. The subspaces this and R2 of the space, R2 of the vector space R2 are called trivial subspaces. So what are trivial subspaces? So in general, I have V is a vector space, V a vector space. Then the subspaces V and just the 0 vectors. So space consisting of 0 vector, these two are called trivial spaces. All right, fine. So I would like you to understand that they are trivial basically because I'm not getting any other information, any other subsets and things like that with a subspace. Fine. Another example 3, similar to whatever we have done. So W is all X belonging to R3 such that 1, 1 minus 1 times X is 0. This is a subspace. Similarly, I can have another subspace which is X belonging to R3 such that 1, 1, 1, 1 minus 1 minus 1, this matrix times X. So X here is X, Y, Z. So these are subspaces of R3. This is a plane. Find its normal vector. This is a line. All right. Find its direction cosines, direction ratios. Find its direction line. Find its direction. it easily passes through 0, 0, 0 because 0, 0, 0 satisfies what is the direction of the line that you need to find out. Fine. Fourth, the vector space, if you recall, set of all polynomials in X, all right, of degree less than equal to polynomials in X of degree less than equal to n, and coefficients in R is a subspace of Rx. So this was a set of all polynomials. There was no degree mentioned. Here I'm saying that I'm restricting my attention to degrees less than equal to n. Fine. One example of which is not a subspace. I would like you to try lots of them for yourself. So take any x belonging to R3. So look at all this set W such that 1, 1, 1, 1 minus 1 minus 1 times x is equal to 1, 2. This is not a subspace of R3. So look at the definition. I would like you to see that this is not a subspace, and why it's not a subspace, try to prove it yourself. Is that okay? So important idea. All right. So let me write the definition of now what is called a linear span. So we have got these calculations. If you see, we have used these ideas of multiplying like this, alpha times this plus beta times this. All right. Fine. Similarly, here also we did these calculations using alpha and beta and things like that. Fine. So that is the idea of what is called the linear span. So definition of, so let me just give you a definition of how do you check whether something is subspace or not, and then I'll look at the definition. Let V be a vector space over F and W का non-empty I'm writing again empty subset of V. Fine. Then W is called a subspace of V if and only if U comma V belongs to W implies alpha U plus beta V belongs to W for all alpha beta belonging to F. All right. So we have been able to take care of alpha times something in beta. So what we are looking at is that U and V is a fixed vector. Look at all its multiples, alpha times that. So I get a line passing through origin and V. I have W. So what I do, V here. So a line passing through 0 and U is already now, I already have. Then I look at line passing through 0 and V, and then look at all its sums and things like that. Fine. And I took U and V from W. I can take another set of vectors from W, and I keep doing all these calculations. I get what I want. Fine. So that's important for us.